Right, the last thing we want to look at in our section on probability is what's called conditional probability. And conditional probability is when you already know something about the events. So the conditional probability of a certain event A, given that B has already happened. So that can change the probabilities. So the formula is actually this: A/B. So that means probability of A given that B has already happened. So the second one is what's already happened. The first one is the probability we're trying to find. And it will equal the probability of the intersection of those two things divided by the probability of B. Or, equally, you could use the number of events if you're looking at the sample space, so the number of events in the intersection divided by the number of events in B itself. Now, if it turns out that that probability is the same as just the probability of A by itself, then we must have independent events. Because what we're saying is, well, actually, the fact that B happened didn't affect the probability at all. So the two events must be independent of each other. Another way of looking at that is if you find probability of A intersection B and you get the same as probability of A times the probability of B, then again, these must have been independent events. So we've got a mixed language class, just like when we were back in year 7. We've got students that are studying French, Latin and Japanese. And so there's our Venn diagram illustrating how many are doing what? What's the probability that a student who studies Japanese also studies French? Well, when I've got the diagram, have a look at what we said. It was the number of items in the intersection. We're looking at French and Japanese. So there were 3 in the intersection. Over the total in B, total in the one that's actually happened. So the one that's actually happened in this case was Japanese, and there are 10 in the Japanese one all up. So 3 in 10 chance is what we're looking at. I suppose if you think about it logically, what we're really saying is the sample space now isn't the whole universal set. The universal set just becomes Japanese, because we're saying, given that they study Japanese, so we're only interested in the students that study Japanese. So our universal set is now just the J set here. And so again, we can look at that and say, oh, well, in our set of 10, only 3 are studying French. There's another way of thinking about it. We've got 2 boxes. They each have got 4 stones in them. The only difference between these stones are some are a different colour. So in box 1, we've got 4 black stones. Box 2 has 2 black stones and 2 white stones. So the first part of this, they've said, well, we're going to choose a box at random first of all. Then we're going to pull a stone out of it. What's the probability that the stone we draw out there is black? Well, it would be this. Imagine, I haven't drawn the tree diagram, but imagine that we had. Our first choice is which box. Now, if I chose box 1, well, all of them are black. So there's a 1 in 2 chance of me drawing box 1, but then it would be times the probability of 1, because now it's a certain event. I must get a black one out. Plus, so the other thing that could happen is I could have selected box 2. Well, there's a 1 in 2 chance of that happening. But now, if it's box 2 that I've got, there's a 2 in 4 chance that I pull out a black one. So when we tidy all that up, there's a 3 in 4 chance. There's a 3 in 4 chance. Well, the other way I could have done this is it really didn't matter about box 1 and box 2, because I could have just said, I'm just going to randomly, imagine the 2 boxes were joined together and the wall between them has fallen down. Well, now it's like having just 1 box. So it really doesn't matter which box I pick. It's really out of all the stones I've got. And so I could have said, oh, well, there's 6 black stones out of the 8 stones. So I'm going to pick one of them. What's the chance that it's black? 6 in 8. So I could have approached that problem that way. But now, it's not known from which box the stone has been drawn. So we don't know. Given that the stone drawn is black, so we've drawn it out and I'm just showing you, hey, look, I've got a black stone. You have no idea which box I pulled it out of though. What's the probability that I took it from box 1? So now we're saying, what's the probability of me taking it from box 1 if we know it's a black stone? I'm showing you, hey, I've got a black stone. So probability of the intersection. It was black and in box 1 over the probability of being black So if I do it via the probabilities rather than the number, black and box 1, well, that was the one that was just a half. Remember, we said if we're branching off on that one, it was 1 and 2 times a certain event of 1. And probability of being black, we just worked out, was 3 and 4. So there must be a 2/3 chance of that happening. So in a particular school, 55% are male, 45% are female. Of the male students, 13% say Monday is their favourite day, whilst 18% of the females say Monday is their favourite. Find the probability that a student chosen at random is male whose favourite day is Monday. Well, we know the probability of male is 0.55, 55%. We know that to be true. So we're now saying probability of a Monday, given that it's male. Well, we know that. That's the 13%. We're saying of the male students, 13% is Monday. So the probability of them liking Monday, if we know they're male, would be 0.13. So these are the two probabilities that I know. So I can use this same formula now, but I'll end up rearranging it to find the probability that we end up with a male and they like Monday. So the intersection. Sub in what we know. Monday, given that they're male, was 0.13. So, and then on the bottom of the fraction on the other side, probability that they're male, 0.55. Rearrange it, and we end up with a probability that we've ended up getting a male who likes a Monday. And we get 0.0715. So that's rearranging that conditional probability formula. Okay, let's play.